Good morning, everyone. Let others join others, inform others also if you can. The Thursday class I am going to take for your analysis of structure 3. I told you in last class also, right? For section B on Monday I'll be taking. For section your section I'll be taking on Thursday. Third period, and yeah, in your timetable please correct it in your timetable. Please correct it because I think you have in your first class you are having analysis of structure, right? But since I'm already having a class in section B, that's why what we are doing, uh, third period you are having OCF, I think. So that OCF will be on your first class, and that means Vishwadeep sir is going to take your first class on Thursday, and third class I'm going to take. Okay. So there was some misunderstanding today. Actually, it was already discussed, but maybe due to Vishnu sir may have forgotten. So now he had a class, so I'm taking that class, and on from next Thursday he'll be taking Vishnu sir OCF will be on your first class Thursday, and third class AOS. Okay. Section A. I think we should start the class, or are some students still there to join? Maybe. Okay. Last class in the AOS, I think AOS class we have taken. I have taken with you all. Started the AOS class, na? We have started the AOS class. This is the second class. Yes. Section A. Yes or no? Please answer. Am I audible? And then this is the second class with you all for analysis of structure, or this is the first class? I have started with the plastic analysis in analysis of structure with you all. Yes, please. Okay, then I think in section B we have started with plastic analysis. Okay, okay, okay. So this is the first class for analysis of structure, and I'll be discussing with you all the last chapter, which is your this one, the plastic analysis. Okay, so okay, okay. So we'll start with the plastic analysis. Okay, the last chapter I'm taking your last chapter. I'm taking your last chapter, which is your plastic analysis. So actually, what do you mean by plastic analysis? I don't have any notes with me now because I'll just simply give you some definition here. I can type for you all here. Okay, so if I talk about this one, what do you mean by ITION? What do you mean by your plastic analysis? Why we do plastic analysis is actually can be defined as the analysis in which the criteria for the design of structure is the ultimate load. Okay, the we design all the things by all the design the structures with the considering the ultimate load. Okay, we also can define it as the analysis of inelastic material. Okay, beyond the elastic limit. Okay, which we will observe here on the stress strain curve. We have, you know, already the stress strain curve. Wait, somebody is waiting for unlock the meeting. Okay. You already know this. The stress strain strain curve. You know already these things. These are your elastic zone. This is your elastic zone from here to here. Since we already know this is elastic zone here, that means whenever any in a material or in anything, when we give some loads or deformations, when we give some forces, they deform and then they again come back to its original shape or original size, then that means they are elastic zone. On the elastic zone, but after that, after this point, after the elastic point, what happens? These are all plastic limit. The material goes into a plastic limit where it does not come back to its original shape. Okay. You can, if I write here, what do you mean by plastic analysis? You will have like, you can write here, okay, PLAS. Yes. Is defined as the analysis in which the criterion for the design in which, okay, that is in which the criterion for the design of structure, structure is the ultimate load. A ultimate load. Okay, that means we can define it as the analysis. Okay, so we can define it as what? We can define it as the analysis of inelastic materials. That is, we study beyond the elastic limit. Beyond this elastic limit, we study, that means which is observed in our stress strain graph. Okay. Actually, what you know, your plastic analysis is derived from a simple mode of failure, okay, in which plastic hinges are formed. Right? That means actually the ultimate load is found from the strength of the steel in the plastic range. We why we do this plastic analysis? Because when we do this plastic analysis, we are actually, the ultimate load is found from the strength of the steel in the plastic region. Okay, when they are, how we can find out that this steel has the, what is its ultimate load? How you can find? By doing the plastic analysis only, because after that it does not regain its original shape, but it will get deformed or it will get yielded. So that means that's why we do the plastic analysis. Okay. Because and also this plastic analysis is quite rapid and has rational approach, okay, for the analysis of structures. It will control the economy regarding the weight of the steel, since the section required by this method are very small. We can take a small section and then we can take a small section and then required by this method are smaller, and those required by the method of elastic analysis. It has its own application. This plastic analysis has its own application in the analysis and design of the intermediate structures. Okay, actually, the basics, if I say you, the basics, basics of plastic analysis. What is the basics actually? The basic of plastic analysis. our this plastic analysis is usually based on the idealization of stresses perfectly plastic. The basic is what that the basic it is what it is usually based on the idealization of stress strain curve as the perfectly plastic. We assume it to be perfectly plastic and then we design accordingly. In this design, what we do in this analysis actually, in this analysis, it is assumed that the width, 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 that is the thickness, width to thickness ratio of plate element is small, so the buckling, local buckling does not occur. Okay. In this analysis, in the basic analysis, what we do in this basic analysis, it is assumed that the width to the thickness ratio of a plate element is small. Why? So that the buckling does not occur. Okay. Keeping in mind, we will keep in mind these assumptions. Okay, keeping in mind this assumption, what we'll do? Wait. Keeping in mind this assumption, you can take a screenshot or something of this. Okay, I don't have the note here, but I'm just typing for you all. So, keeping in mind this assumption, what we can say, it can be said that the section will reach its plastic moment capacity, and after that, will be subjected to, right? And after that, यहाँ पे subjected to considerable moment at applied moments. Okay. So this was your basics, plastic limit analysis, plastic analysis. What it says that the plastic analysis is usually based on the idealization of stress strain curve is perfectly plastic. In this analysis, what we do, we assume that the width to thickness ratio of the plate element is very small so that the local buckling does not occur. Okay, keeping in mind what happens, this assumption, keeping in mind, we'll keep in mind this assumption and it can be said that the section will reach its plastic moment capacity and after that will be subjected to considerable movement and applied moments. Okay, and what happens if we see what are the basic, actually the basic principles, PRINCIPLES, principles of plastic analysis. Okay, there are following conditions for plastic analysis. Okay, and there are what? The number one is your mechanical condition, MECHANIC, mechanical condition. Next is your equilibrium condition. Third is your plastic moment condition. Okay, so plastic moment condition. Condition. Okay, so basically what happens, your principle of plastic analysis, there are three conditions basically, which is the mechanical and equilibrium condition. We have the plastic equilibrium also. Okay, if we talk about the mechanism condition, mechanical or mechanism condition, you can say, when the ultimate load is reached, collapse mechanism usually forms. Okay, this condition, the principle of plastic analysis, the first is a mechanism condition where what happens, the ultimate load is reached and the collapse mechanism is usually formed there. Okay, and the equilibrium condition is what, here summation of fx, summation of fy, summation of movement is all zero here. How I'll show you. I cannot type here the summation word, but I have to write. So a mechanism is what, where the ultimate load is reached. Then we have the equilibrium condition where the summation of x, summation of y, summation of moment, summation is zero. Okay, plastic moment condition. What is this principle? Here the bending moment at any section in the structure should not be more than. Wait, I'll just type it for you. For the for the okay, for the plastic moment condition. Okay, here what happens, the bending moment bending moment at any section in the structure should not be more than the full plastic moment. That means what, moment at which plastic hinges form and structure moves to failure of the section. Okay, full plastic, that the full plastic moment, that means what I'm telling is moment at which plastic hinges form and structure moves to failure of the section. Okay, so here what happens in this principle? This principle says what? That in the plastic moment condition, the bending moment at any section in the structure should not be more than the full plastic moment. That means the moment at which the plastic hinges form and also the structure moves to failure. Okay, is called this plastic moment. This is the condition, plastic moment condition. That means if we consider the case of simply supported, you can see, when we consider a simply supported beam, suppose we have a simply supported beam here, then what happens, when the load, when we are giving a load here from the top, suppose this is a simply supported beam here and we are giving a load from top, what is happening, when the load is gradually applied on it, bending moment and stresses increases. That means as the load is increased, as this load is increased, the stresses and fibers of the beam reach to the yield stress. If I show you, Suppose this is a simply supported beam. Here from the top, if we increase the load, then what happens when the load is this load? Here, this is simply supported beam. Consider this as a simply supported beam. Okay. When we give a load from top, what happens? When the load, this load is increasing gradually, what happens here, the bending moment and the stresses also increases. And again further, if this load is increased here on the beam, above the beam, the stresses in the fiber of a beam reach to a shear stress. That means what, at this stage the moment which has converted the stresses into the yield stress is said to be plastic moment. Okay, so what is your plastic moment? So what is a plastic moment? When the loads on this, simply suppose when this loads on a simply supported beam is increasing, the stresses here on this fibers, here on the fibers of the beam reach to the yield stress at this stage. That means the moment has converted the stresses into the those. So when the load was applied, right, when the load was applied here, what was happening, the stresses was developed here. That means when the stresses were developed here, what happened again, the further increase of this load here, has there was a moment at this stage. What happens when furthermore this load was increased, what happened, the moment at this stage when the moment is converting this normal, simple converted the simple stresses to yield stress, that is known as your plastic moment. Okay, that is known as your plastic moment. The moment which converts the stresses here on the fibers of the beam into yield stress, then this moments are known as your plastic moment. That means it is usually denoted by MP. Okay. That means at this stage, when your normal the fiber stresses has been converted into yield stress, then that means the beam member cannot take up any additional moment, but may maintain the moment for some amount of rotation and acts like a plastic hinge. Okay, that means hinge means having no capacity to resist the moment. Okay, if this simply supported beam acts as a hinge beam, then that means what, the having it has no capacity to resist the movement. Okay, plastic hinge behaves like an ordinary hinge. Okay, allowing free rotation here about its own axis. Okay, so this is known as a plastic moment. You understood what is a plastic moment, why we are plastic analysis, why we are doing plastic analysis. We need to find out the plastic moments, because this plastic moment means what? This is converting the normal stress into the yield stresses, and because of which what happened? Because of this, the beam member cannot take up any additional moment, but may maintain this moment for some amount of rotation here, and it will act as like it may act like it's a plastic hinge, which means there is no resistance, there is no capacity to resist this moments. Okay, then why this plastic moments, we have to calculate these plastic moments, right? So to calculate these plastic moments, the term shape factor has its importance, has an important role to play. Okay, why shape factors can be defined as, what is actually shape factor? Shape factors is defined as a ratio of the um let me note it for you. If I write here, I'll not write here, I can write here, I'll write here. Okay, so, what is a shape factor actually? Shape factor can be defined as the ratio of the, suppose this is your shape factor SF, okay, as suffix F. So, this is your shape factor. Now, what is a shape factor? Shape factor is defined as the ratio of plastic moment to yield moment, yield, yield, moment, yield moment. Okay, so your shape factor is what? Your shape factor is plastic moment divided by your yield moment. It is the ratio of the plastic moment to the yield moment Okay, and this shape factor depends usually on the shape of the cross section. That means it can be your, it depends upon the shape of your, like it can be circular, it can be rectangular, it can be it can be T section, etc. Okay, so I think, oh, I have not taken any class on this now. So we have different shape factors. I think if you know or not the shape factor. For rectangular, it is different. For circular, we have to know the shape factor. For triangular, we have to know the shape factor. For T sections, it can be. So you can take a screenshot of this, and then I'm going to write another new notation, new page where these things will go. It will vanish now. We'll take an example of shape factor. Okay. And why actually we are doing the plastic analysis? You know why? Because in the real life problem, if we see, we know in steel structure what happens. The design is mainly the design main analysis of how much moment can the structure carry is done by the plastic analysis. Okay. The maximum moment of your steel structure can carry, can be determined by your plastic analysis. Okay, so now we'll take, since we have to know for that the shape factors, so we will take, now we will talk about the shape factors. We know already what is shape factor. We have discussed the shape factor is the ratio of the, again I'll take the notations. So shape factor was ZP by ZE. The shape factor was what? Plastic section modulus to the elastic section modulus. Okay, where you know what is your ZP? ZP we are doing so many times on these things. Okay, ZP again trigger, all this we have done. ZP is the plastic modulus, and it is given by A by 2 Y1 plus Y2. Okay, and we have our ZE is given by capital I by Y. Okay, this ZP is A by 2 whole into Y1 plus Y2. That means from plastic neutral axis, there is equal area ratio. Okay, and ZE is what? Here, moment of inertia above centroidal axis. This is the moment of inertia I. ZE is the moment of inertia about centroidal axis. Divide by your, this one, the Y is the distance of the CG. Okay, so we are having what now? We know this thing now. For a rectangular, if we see, if we try to find out the shape factor for this one, suppose we have this rectangular member here. So we have to find out the shape factor for this, right? So this is, suppose there is a, this one. Here is, this is the center. Okay. So now for this rectangular section, if you are asked to find out the shape factor, how we will find out the shape factor? We know the shape factor is what? ZP by ZE. But for this rectangular section, if suppose the depth, if here, if here we have the depth is D, we have the width to be B, this width is B, this depth is D, and here we have this one. Suppose here here. Okay, we have Z. If we see ZP is ZE is what? Elastic section modulus is I by Y. I we know how much. If I show you the, this is what? This is the, these two are two members here. Okay, Y1 we can consider this to be one first member. This can be two second member. So this is y1, this is y2. Distance of this CG from distance of this part, since this is dividing the rectangular section into two equal parts in equal area ratio. So now this is the neutral axis. From here we have this member has this CG which is y1, and this member has this CG which is y2. So now if you see here, what is your ZE? ZE is what? ZE is your I by Y max. I by Y max. So that is how much? Your I by Y max is, I is how much? VDQ by 12. Right? So BDQ by 12. BDQ by 12 by, this is bracket, you can close this. Y max is how much? This Y max is d by 2. The maximum distance of this distance, maximum distance from the bottom is how much? For this depth, maximum is from the CG. From the CG, this is the for the entire body. If I'm talking, this is the neutral axis. The maximum distance from the CG to the bottom portion is how much? This one, d by 2. This portion d by 2 from here to here. So this will be d by 2. Okay. So that means which is nothing but your BD square by 6. BD square by 6. Now this was your plastic section modulus. Sorry. This was your plastic section, elastic section modulus. Now coming back to the plastic section modulus, we have ZP is how much? ZP is given by A by 2 into, we have Y1 plus Y2. Okay. So now you see, what is your area of this rectangular section? Area is B into D. So B into D, this one, divided by 2. Then we have y1 and y2. Now I told you what is a y1 and y2. Y1 is this distance from the neutral axis to the CG, and your y2 is this distance from the neutral axis to the CG. So y1 is how much? This y1 will be how much? This portion is your d by 2. We have known this. This is your d by 2. D by 2. Right. So if this portion from here to here is your d by 2, that means what will be your y1? This is at the center of this. This is a member here, one. This is your one member. This is your second member. So this is your y1, the distance of the CG from the neutral axis, and the distance of the CG of the neutral axis from the neutral axis. This is y2 for this member. So this is how much? This is at equal distance here. This is divided into 2. That means here the center. So if this is d by 2, that means this will be how much? D by how much? This one, this distance from the neutral axis to your this CG of the y1 member will be how much? D by 4. How? If I write here D by 4. This is also D by 4. So that means y1 is this distance, this one. This distance. This is the center. Okay. So we have how much now? We have here d by 4, d by 4. So our y1 is how much? Our y1 is d by 4 plus d by 4. Okay, this one. So that will give you how much? That will give you now your this to be b d by 2 into d by 2. This one b d by 2. And here d by 4 plus d by 4, that means twice d by 4. And that is twice d by 4 means d by 2. Okay, so what we have now, we have C. Our SF is how much now? Our SF will be ZP by ZE. That means we have BD by 4 divided by BD by 6. Sorry, BD square by 4, no? BD square. Okay, okay, cut this one, okay? This one you cut. BD square by 4 we have divided by BD square by BD square by 6. So how much is this? This comes to be 6 by 4. That means 1.5. So for the rectangular section, what we are having for the rectangular section, our shape factor is 1.5. Okay, for our rectangular section, this is 1.5. And similarly, we will have for circular, we will have for triangular, we will have different shape factors. Okay. Okay, we have 5 minutes now. I'll take the attendance. Please give your attendance. Roll number 1.
Roll number 1, present, ma'am.
Roll number 1. Stephanie.
Present, ma'am. Present, ma'am.
Hello.
Yes, ma'am.
Hello. Hello. Roll number 1,
Present, ma'am.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12,
Present,
13,
ma'am.
12,
Present, ma'am.
12 present, 14,
Present, ma'am.
15, 17, 18, 19, 20, 20, 21, 23, 24, 25, 26,
26
26,
present, ma'am. 26 present, ma'am.
okay, 27, 30, 30, 31, 32, 34,
34 present, miss.
36, 37,
37 present, miss.
38, 39,
38 present miss.
Present, ma'am.
38, 39,
Present ma'am.
42,
Present, ma'am. 39
43,
present.
43, 45,
45
48,
present ma'am.
48, 49,
49 present, ma'am. 49.
50, 51, 52, 54, 50, 54, 57, 57,
Yes, ma'am. 50 present,
58,
50.
58, 60, 61, 63, 99,
Yes, ma'am. 99.
101,
Present, ma'am. 101.
102, 104,
Present ma'am 104.
106, 108,
108 present ma'am.
109, triple one,
Present ma'am.
113, 113,
Present ma'am.
4,
103.
114, 118,
Present, ma'am.
118, 120,
Present 120.
124,
124. Present, ma'am.
133,
Yes, ma'am. 133.
134,
Present, ma'am. 134.
136, 143, 144, 145, 149, 151. Okay, those who I'll inform you whoever is absent, and then you can just
Ma'am,
inform.
145.
You can inform me. 145. You can inform me whoever is present or absent. Okay, thank you for today.
Ma'am, roll number 30.
Roll number 30. Okay. Okay, thank you.